Welcome to this demo of IRBCAM 8-axis machining. The industrial robot has 6 degrees of freedom, the linear track has 1, and the rotary axis over here has 1 degree of freedom. The first step is to load an Apt file. Apt is a tool path file generated by CAM software. This Apt file contains 5 degrees of freedom. Once this toolpath has been loaded into IRBCAM, we can go at View, Combination View, and have a look. Here's the XYZ toolpath, the XY view, the XZ view. By clicking over here, we can see the cutter vector here as a red vector. This shows the angle which the cutter will approach these targets. The red color over here means that these coordinates have not yet been configured. They contain the 5-axis data from the Apt file, but we need to add 3 more degrees of freedom, 1 for the robot, 1 for the track, 1 for the rotary axis. The first step we do is to edit the object frame. If I zoom in on that object frame, it sits right in the middle of the rotary table. The blue vector is the Z-axis, red is the X-axis, green is the Y-axis. We see here that the toolpath goes to Z equals 0, to the origin, which means that we are dangerously close to this plate of the rotary axis table. Hence, we would like to shift that one out, for example by 300 millimeters. We shift the origin of the object frame 300 millimeters out from the rotary table. Then I go Tools, Configure Path. It's currently red here, which means that the robot is not able to reach this first coordinate. But if I change the rotary axis angle from 0 to 180, we can see now that this square turns green, which means that the robot can reach, as we see also here. But we don't like this configuration of the robot, so we can also change the 6th degree of freedom on the robot, the tool roll angle. So if we make that one 90 degrees, we have a better coordination configuration for the robot. Now we want the linear track to move, but only in the negative direction. This is to avoid that the track moves small movements backwards and forwards, which could cause loss of accuracy due to, for example, friction or backlash. Then we change the rotary axis mode from fixed to dynamic. This means that when this table is turning, the robot is going to try and keep the spindle aligned as shown here for the first target. Then we click OK, and IRBCAM starts to fill in the missing 3 degrees of freedom for this system. In total here there are 5,800 targets which needs to be configured. If everything goes well, which it does in this case, all the points over here will turn green, which means that they have been configured. We can then scroll down the list and see. We see now that the table is turning, the linear track is moving, and IRBCAM is trying to keep the spindle orientation constant. If we scroll further down, and then I zoom out from this view, we can see what happens at the end of the toolpath. Here, because we are getting so close to the origin and the toolpath is quite steep at the end, IRBCAM has to tilt the tool in order to reach the target. So it's tilting now sideways. This is the YZ plane it's tilting. But IRBCAM is keeping this angle in this plane, in the XZ plane, constant. So we go all the way to the end, and the entire path has been configured. We can then go View, Rotary Axis. We see here that the rotary table is doing 180 degree movements from 0 to 180 roughly. This red target or symbol here shows the current position of the rotary axis. We can go view linear track, and again this red circle shows the current position of the track. And because we chose negative movement only, we see here that it starts at 5,662, decreases to 1.6 meters for the track, and only in the negative it's constant or negative movements only, which will give us a good accuracy for this track motion. The last step then is to export the Rapid code. If you go to Rapid Options, we see that we've chosen the rotary table axis as number 7, the linear track as number 8. So Rapid, save Rapid. And now it's generating a fully configured Rapid code, which we will see later in the final output. It will contain XYZ and the quaternions for the robot, the table angle, the linear track position, and also the 4 numbers for the configuration. If I open the Rapid code here, we see here we have X, Y and Z, 4 numbers for the quaternion, the configuration numbers, the rotary angle, the linear track position. This code could be inserted now directly onto a robot controller, and this code should work with S4, S4C, S4C Plus and IRC5 controllers.